In this video, we're going to investigate pH. pH and the pH scale is something that you've probably all heard of, but we're going to look at it in a little bit more detail and look at how we do calculations involving pH. pH allows us to quantitatively measure the concentration of our hydronium ions and gives us a way to basically to look at how acidic or how basic a solution might be. The pH scale goes from 0 to 14. A pH that is less than 7 means that our solution is acidic. pH greater than 7 means that it's a basic or an alkaline solution. pH of 7 itself means that it's neutral. Blood and intracellular fluids typically have a pretty tight pH range of about 7.35 to 7.45. If the pH of blood is above that range, that's a condition called alkalosis. A pH below that range is called acidosis. Both of those can absolutely be life-threatening conditions. And so in a later video, we'll look at how some of the tools that essentially that our body uses to make sure that our pH stays within that range. This here just gives an idea of the pH range of some typical bodily fluids. Gastric fluids, stomach acid, pH of 0.5 to 2. Very, very, very strongly acidic, very corrosive type of pH, which it needs to be. That's where digestion really starts, is by that gastric fluid breaking down our foods. Urine, pH of anywhere from 5 to 8. And saliva, 6.5 to 7.5 or so, and so forth. You can see the typical range of some of these different fluids. In order to calculate pH, we use what we call a log scale. The reason for this is, pull up my whiteboard here. So the big reason for this is that the hydronium ions can exist in a wide range of magnitudes. We might have a hydronium ion concentration that's maybe somewhere around 0.1 molar. We may find concentrations that are more like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 0.1201 molar. And so we get this very wide range of potential magnitudes for that hydronium ion concentration. Some other terminology, by the way, that I don't think I introduced when I talked about molarity. When you see brackets like this, and so in this case, brackets of our H3O plus or brackets of the H plus, remember, fundamentally, those really mean the same thing. But these brackets just mean molarity. And so we're talking about the molarity, our moles per liter of the hydronium ion concentration. And so, again, back to the point is, since we can have this wide range of magnitudes, we use a log scale in order to calculate pH. And so the pH of any solution is equal to the negative log of the H3O plus concentration. Now, don't worry too much about the math of that. Just know that we do use what's called a logarithmic scale, which is a base 10 scale. What this really means is that a change in one pH unit is really a 10-fold change in the hydronium ion concentration. And so, for instance, if you have something that is a pH of 2 versus something that's a pH of 5, this solution that is a pH of 2 is actually 1,000 times more acidic than the item with a pH of 5 because it's a log scale. And so we can go up even. A pH, something that's a pH of 4 is 10 times more acidic. pH of 3 is 100 times more acidic than something with a pH of 5, and so forth. That's what a log scale really does for us, is it works in orders of magnitude like that. As far as putting something like this into your calculator, it will depend on what type of calculator you're using. Say we want to calculate the pH of a solution with an H3O plus concentration of 0.025. Using a calculator like this, you would put in your 0.025, then hit your log button. Then we want the negative of that. So that solution would have a pH of 1.6. If you've got a TI calculator, then you can literally put it all in at the same time. So I would go negative log of 0.025. Clear that out, so that's the only thing on my screen. I'll show it to you. So negative log 0.025 would look, there you go, just like that. Negative log 0.025. And we get our pH of 1.6. So again, just depends on what type of calculator that you're using. Make sure you are using it properly so that you can calculate your pH correctly. But so back to the log scale, since a difference of 1 pH is a 10-fold change, an order of magnitude difference, this means that if the pH of your blood changes by even just 1/10 of a pH unit, that can be fatal. And so the pH of your blood has to be kept within that very narrow window. We have something called the auto-ionization of water. What this really boils down to is that water, if we view it as HOH, can split up into H plus and OH minus. And we're not going to get too much into the details of that, but this is going to lead us to a couple of different types of calculations. Because in pure water at 25 degrees Celsius, our H3O plus concentration is always 1 times 10 to the negative 7th. And remember, that is what leads us to. So if our H3O plus concentration is 1 times 10 to the negative 7th, we calculate the pH of that, negative log of 1 times 10 to the negative 7 equals 7. And so that's our pH of a neutral substance, pure water. The OH minus concentration is also the same thing. And again, we're not going to worry about the math of this. I'm not going to get into this whole idea of KW in this course. But ultimately, this is what is important for you, is that this tells us that in any solution, the H3O plus concentration multiplied by the OH minus concentration is going to be equal to, it's going to be equal to 1 times 10 to the negative 14th. This means that for any solution, if you know one of these, you can calculate the other pretty easily. So again, H3O plus concentration times OH minus concentration will always equal 1 times 10 to the negative 14th for any solution. And so we can use that. And so here's an example here where we know our H3O plus concentration is 1 times 10 to the negative 6th. And so we could put in this calculation to then find that our OH minus concentration must be 1 times 10 to the negative 8th. So we can, if we know one, we can find the other. And we can see that happening here. This is just how we would rewrite it. Just trying to decide if I wanted to really get into this much. And really all that we're looking at on this slide is that inverse relationship between H3O plus and OH minus. In any solution, the more H3O plus that you have, the less OH minus that you have, and vice versa. They're inversely proportional to each other because of that relationship, that 1 times the other is always equal to 1 times 10 to the negative 14th. I'm really not going to get into that either. So here's a list of some of the calculations. This is our last slide on this presentation, but we might also want to calculate what we call the POH And you might be asked to calculate that. That's just, it's very similar to pH, but now it's a measure of the hydroxide ions. The pOH is calculated very similarly. It's the negative log of the hydroxide ion concentration. We talked about this relationship, our H3O plus times our OH minus is 1 times 10 to the negative 14th. This also leads us to saying that pH plus pOH is always equal to 14. And so these are a whole bunch of tools that basically allow us to calculate the OH minus or the H plus, the pH or the pOH, as long as we know one of these aspects of our solution. And so this has been just a quick introduction to pH and some of the calculations, which should help you out as you do some of the homework for this section. And so that is it for our video on pH. That's the way the cookie crumbles. That's a horrible closing too. And I got tired of you stay classy. But tell you what, this is now our videos for our third week of lecture. See how many of you are really paying attention. Email me what you think I should use for a nice closing statement to our videos. I can choose more than one. If I like more than one, I'll use it. But for anyone that I actually use, I will add 5 points to your midterm grade. So let's see who's watching and who wants to play. So come up with a new closing statement for me. It can't be "you stay classy, USM," or "that's the way the cookie crumbles," because I've already used those. See what you can come up with. Have a good day, everybody.